Welcome, everyone, to today's Quantum Marketplace. I'm Celia Merzbacher. I'm Executive Director of the QED-C, and I'm delighted to be kicking off 2025's Quantum Marketplace program with today's webinar on fabrication and prototyping services for quantum. I think this is a critical area and sometimes unappreciated or underappreciated by those who are focusing on the applications and use cases of quantum. Without fabrication and the ability to make and test and improve these systems, it's not going to happen, or it's not going to happen as quickly. So we'll be getting to a great lineup of speakers shortly. I just wanted to welcome everyone and remind you, for those who are perhaps new to Quantum Marketplace, the program is really aimed at showcasing what's going on in the community. QED-C has a very broad cross-section of members, and Quantum Marketplace was created as a way to spotlight and showcase what's going on in the community. So this is the first or the next in a series of webinars that's been taking place over the past several years. We've had over 30 events to date with more than 165 participants. If you go to the next slide, I think it just highlights some of, and next, what Quantum Marketplace is. It's about raising awareness, as I said, and it's also making it possible for connections to be made, which is really another mission of QED-C, making collaborations, partnerships, and ultimately creating new business for QED-C members. Next slide. So the Quantum Marketplace has got its own webpage on our public-facing website, and there you can find sort of two sets of information and resources. One is a list of all the companies in QED-C. They're sort of searchable and sortable. And for each of the companies that has participated, you'll see a small camera icon next to their name, which means they've got a video that's been uploaded, and you can go and learn more about the company. And there's a link to their website as well. So that's one resource. Another is the recordings of the entire webinars. And over on the right-hand side, you can see the screenshot of the way that you can kind of sort through those, see what the past programs have been on, and watch them after the fact. So if you know somebody who perhaps in your organization or in your network who you think might be interested in learning more about quantum and the state of the art, please feel free to forward them the link to these resources. So next, I'll just remind you that, as I said, the recordings will be made available. They're made available on the QED-C website and also on our YouTube channel. So it's easy to find us, and we're excited, as I said, to be hearing today from 4 organizations that are in the fabrication and prototyping services area. So with that, welcome, and I will turn it over to Julie Burt from SRI, who is going to be host for today's program. Julie, over to you.
Thanks so much, Celia. Really appreciate it. So I'm going to give you guys a little bit of an overview of where we're at in the prototyping and fabrication market before I introduce our 4 speakers. So since 2021, when we last discussed this topic, the quantum fabrication services industry has made substantial technical progress. Specifically in the superconducting qubit space, fabrication technology has matured to the point where we are starting to see full quantum processing units come online and be both available for purchase and for use as a shared service. Superconducting qubit processors made headlines in 2024, with Google announcing its Willow chip that demonstrated below threshold quantum error correction, a breakthrough achievement that has given a significant boost to the quantum computing industry, which has been reflected in the share prices of those quantum computing companies. These events demonstrate the rapidly maturing commercial status of superconducting qubit manufacturing and has refocused many players in the fabrication and prototyping services industry towards other more emerging markets in the alternate qubit systems, spin qubits, optical qubits, and V-center qubits, topological qubits, and quantum limited amplifiers, and the broader emerging field of quantum sensors. Our panelists today represent all entry points in the prototyping market today, with Rigetti offering full quantum processing units, VTT Technical Research Center Finland providing co-development, scaling, and technology transition in quantum sensors, quantum computing, and quantum algorithms, TNO Dutch National Research and Technology Organization providing early stage prototyping and development services for alternate qubit architectures, and SRI providing innovation services focused on developing new quantum sensors using trapped ions, photonic integrated circuits, and compact laser sources. So the lineup for today, we have 4 speakers, each from those respective organizations. The first speaker is Yuvrav Mohan from Rigetti Computing. Yurav is the lead quantum technology program manager at Rigetti Computing, focusing on quantum processing unit system integration, business development, and growing the quantum computing ecosystem. He's been at Rigetti for over 8 years and has experience across the stack as a former senior quantum engineer. His background is in material science, physics, and nanotechnology, and he's currently pursuing an MBA at the UC Berkeley Haas School of Business. So I'll turn it over to Yuvrov, who will give us his 5-minute presentation.
All right. So just a quick introduction to Rigetti. So we are a full stack quantum computing company. Our mission is to build the world's most powerful computers to solve some of the most challenging problems that face humanity today. Everything from logistics to pharmaceuticals and you name it. Just a quick snapshot of our product offerings. They run the gamut from full quantum computing systems all the way to application services. This is quite a bit expanded since the last time I presented here at the Fabrication Services workshop. Today I want to focus on this second box here, our QPUs and Foundry services. I am happy to talk about any of the other boxes offline, but in the spirit of fabrication and hardware, I want to focus here. So our hardware offerings, I would say they're kind of bifurcated into these 2 categories. One is our QPUs. So these can range from our 9-qubit system, termed Novera, all the way up to 84-qubit systems, which we have deployed over the cloud. But people can actually buy these. So if you're a national laboratory or you're a university that you want to get your students up and running with small-scale QPUs, this is a great place to start. Many of you who have been keeping track of our Foundry services already know about our fabrication services, but I'll touch on those briefly. So we do have Foundry services where folks can submit their own superconducting quantum device designs, and we will fabricate them for our customers. So underpinning a lot of this hardware is our Fab 1. So this is our purpose-built superconducting quantum circuit manufacturing facility. It's based in Fremont, California, in the Bay Area. And really, this Fab 1 underpins a lot of our hardware development that's gone on the past few years. A couple of key things that enables us to do is we call this hardware innovation flywheel, where we design a chip, fabricate a chip, and test a chip. And we can do this with significantly faster cycle times than your typical CMOS or MEMS foundry is able to do because of the vertical integration. This vertical integration and having this fab in-house also minimizes a supply chain risk. It drives a lot of the efficiency in scaling our architecture, which if you've been paying attention to our roadmap, it will heavily utilize our pioneering chiplet technology, where we're taking multiple dies and making a unified quantum processor out of those dies. Probably most importantly for this forum is our R&D partnerships that this enables. So we've been able to leverage Fab 1 as an asset to deliver value towards or to our customers and our partners, which range from national labs like Fermilab and Air Force Research Lab to universities such as Purdue University and others. So you might be wondering, why Foundry Services? Why offer your fabrication facility to the outside world, right? This is a key piece of our IP. But really, it comes down to the parameter space of research problems in the quantum hardware area are just too large for any one organization to solve on their own. So we really wanted to enable these researchers in academia and national labs and other companies to focus on these problems of interest, whether it's new qubit geometries, new gate schemes, new coupling schemes, maybe different kinds of amplifiers from GPAs to tupas, etc. And remove the fab aspect from the fab variability aspect from there, right? So if you're working at a university clean room, these tools are shared. You don't know if someone's put in, gold or some other, some dielectric material before you do your processing. So removing that variability is a great boon to these researchers that aren't focused on the fab aspect of things. So in doing so, we want to help accelerate quantum innovation, across the board. So I also wanted to give a snapshot of what is possible. So, these left two columns are what we would call our prototyping services in a sense. So with our foundry, like I mentioned earlier, we have a PDK, a process design kit, that has layer definitions, what corresponds to what metal, what certain features are fabricatable and what aren't. So folks can submit designs, we can allocate these designs onto a multi-project wafer, and then manufacture the devices for our partners and customers. For the Novera, so this is actually relatively new. We launched this in December of 2023. And really, it's, I would say we've seen the market around this develop kind of in three different areas. So one is other quantum companies. So folks that are developing quantum software or control electronics. At some level, they need real QPU hardware to run on. And there's only so much you can do over the cloud. It really helps to have your own system, behind your own firewall, very tightly integrated with your own computing infrastructure. Second is the academic market. So these are schools of engineering or departments of computer science that want to host a QPU. They want to get their students learning on it, not just from an algorithm perspective, but also from a hardware perspective, right? What sort of mechanical engineering considerations go into building this whole system? A QPU is much more than just a chip. There's a lot of cryogenic components involved. Of course, there's the dilution refrigerator, but there's also amplifiers, signal conditioning components, the room temperature control electronics that actually deliver the microwave pulses to control your QPU. All of this can be manipulated and swapped in and out and customized. So really, this Novera is a really good prototyping platform for a full quantum computing system. And then you can add to that as well. I mentioned larger scale systems like 2484 qubit. We've demonstrated that at the NQCC in the UK, where they are customizing essentially the combination of fridge, control systems, chip, and so on. So I'll stop there. I think I'm close to my 5-minute time, but yeah, to highlight, Foundry services and Novera are really, really powerful, we think, for the field in terms of driving research forward and enabling people to get their hands on quantum hardware and increase the pace of learning and workforce development. Thank you.
Great. Thank you. Thank you, Yubrav. Quick follow-up question. With the new access to quantum processing units that you're making, if a user wanted to purchase or use one of those shared facilities, what kind of expertise might somebody need to effectively work with one of your systems?
Yeah, great question. So the Novera is intended to be as plug and play as a QPU can get. So as long as you have an existing dilution refrigerator and room temperature control electronics, you can get up and running. We've also launched a Novera partner program to create an ecosystem involving other vendors. So, from Bluefors, Maybell, Oxford for the fridge piece, and then Quantum Machines, Qblocks, just as an example of the control systems vendors. So really, even if someone doesn't have these existing pieces, we help them get up and running. They can kind of build your own quantum computer, so to speak. From an expertise standpoint, I think having at the very least some experience with experimental physics, how to operate cryogenic systems is helpful, but maybe not strictly necessary. But yeah, we want to really lower the barrier to entry for quantum for folks from diverse fields.
Great. Thank you so much. All right. I am going to now introduce our next speaker, Jordan Sr. from VTT. So Dr. Jordan Sr. is the research team leader for quantum computing hardware at VTT Technical Research Center of Finland. His work currently focuses on developing a superconducting pilot line initiative aimed at developing higher reliability, high reproducibility, and high-yield fabrication processes for 3D integrated superconducting quantum chips and devices, as well as developing new cutting-edge technologies for both enabling and scaling up quantum computing. With that, I will hand over control of the presentation to Jordan.
So thanks for the introduction, and I'm delighted to say what we're doing in quantum technology at VTT. Okay, there's already the introduction on what we do, but there we are up in the north of Europe. We're 100% owned by the Finnish government, Ministry of Economic Affairs and Employment, so in some sense a government research lab, where we do research, development and innovation for our partners, with a turnover of about €250 million, half of that coming from abroad. And we've been at it for about 80 years with around 2,000 employees at the moment. And where do we sit in the innovation platform? Well, we try to be in this sweet spot between what the universities are doing in the basic research, so chip scale, one-of-a-kind proof of concepts. And we try to take that and make it into a scalable, hopefully at least wafer scale and reproducible technology that can be applied for the customer's applications and then transfer that into the industry. But we also work the other way around. So we can work with our industrial partners and do more cutting edge or high risk research projects. And we try to be in this sweet spot where we think the real innovations are born and nurtured. So in short, what do we do? Well, we have all the necessary experts, around 250 of them, about half of them with PhDs, across the spectrum of microelectronics and quantum technologies. So we do everything from 6G technologies to various sensing solutions, all the way to quantum hardware, mostly superconducting quantum hardware and some photonics at the moment. And recently, together with IQM, we have co-developed 2 in-house quantum computers with a third one on the way. And we offer those with our partners to develop quantum algorithms and software solutions. So we really span the whole gamut of microelectronics and quantum technologies, and of course develop quite a large IPR portfolio as part of that we are constantly licensing out to try and make impact. It's also worth saying we operate the largest R&D clean room in the Nordics, that we are happy to work with our partners to develop their solutions. Speaking of solutions, so superconducting qubits, we are mostly working with these aluminium Manhattan-style transmon qubits that are quite popular in the community at the moment. They seem to have the highest demand at the moment for let's say, our fabrication services, and our coherence times seem to be around this few hundred microsecond range, which seems to be reasonably okay. But we are not super happy with that. We are trying to develop technologies to go beyond aluminium, to go beyond the liftoff process, maybe with some X junctions, and to make them more compatible with going to high density, for example, through 3D integration. Speaking of 3D integration, we believe we have one of the best offerings in Europe in terms of our superconducting 3D integration platform. So we have superconducting through silicon vias on a 6-inch platform, and also superconducting flip chip. And we're developing various other technologies like solid state cooling and so on that we think will also be useful for the field deployability of QPUs and quantum technologies with superconductors. We also do quantum sensing. In fact, this is the oldest quantum technology at VTT. So for the last couple of decades, we've been developing squids for medical and space applications, and also SNS PDs. These have seen quite a boom in recent years with lots of material development going on. And perhaps the most exciting topic for me personally is that we have a 6-inch wafer process for superconducting graphene, where we've been able to make Josephson FETs and bolometers with this technology. And we're actively looking for partners to commercialize this. We also have some cryogenic electronics. So we have a lot of experts working on, let's say, higher frequency, the K and W band applications. And we've been developing cryo-CMOS and silicon germanium techniques for making cryogenic electronics. And we believe we have one of the best low noise amplifiers in the W band, which may be of some interest for future quantum technology developments. I'll also advertise that we have ultra-low loss silicon insulator photonics platform that we are constantly developing, and various optical packaging solutions as part of this that we are offering to all of our partners if they are interested. So how do we work together? It's typically through these comprehensive research and development projects where we can do design services, fabrication services, and measurement services, whether that's on the prototype level or even low to medium volume manufacturing. And that's really what I wanted to say in these 5 minutes. So if you're interested to collaborate or co-develop something, please do get in touch.
Great. Thank you so much, Jordan. One follow-up question. You mentioned one of VTT's strengths is helping companies go from single devices to full-scale wafers to enhance the repeatability of their processes. How do you help companies achieve that type of scalability?
I think ultimately that comes down to two things, right? You can either design your prototype chips to be scalable from the start, which many people do, but you also, as part of that, need to know that you need to understand your processes, and you need to trust them, understand the tools, and be able to perform fabrication at enough volumes that you can have some control over the scalability and get the statistics to know that you are stable. And let's say, usually in the kind of CMOS and semiconductor industry, you would just trust that some foundry already can do this for you. They already have a solution. They're already producing many wafers per minute, that they have stable processes. But we don't really have that for many of these technologies in photonics and superconductors. So we try to be this intermediate partner to try and make it ready that the foundries, when they are ready to take it on, can adopt our processes. That's where we like to sit.
Wonderful.
Hope that answers the question.
Wonderful. Thank you so much, Jordan. All right, so I'm going to move on to introducing our third speaker, who is Roger Verburg. Dr. Roger Verburg holds a PhD in experimental physics from Leiden University. At TNO, the Dutch National Research and Technology Organization, he worked on EUV lithography with ASML and Carl Zeiss and became a principal project manager. From 2013, he was co-founder of the QTech Research Center for Quantum Technologies. And since 2016, he is the director for semiconductor quantum technologies and medical photonics at TNO. He is active as core team member of the Dutch National Roadmaps for Nanotechnology and Semiconductor Equipment and the Strategic Advisory Board of the European Quantum Technologies Flagship and Supervisory Board member of Quantum Delta NL. He co-authored the National Quantum Agenda, National Growth Fund proposals such as NXT Gen, High Tech and Quantum Delta NL, and national strategic programs for top sectors such as semiconductor equipment. And Roger, I'm going to let you take over the share.
Thank you very much for this opportunity to tell a few things about our portfolio. So a little bit not uncommon to VTT. We're not a for-profit organization with, in fact, two assignments. To the left, an example of our contract research to support companies to innovate, and a picture on the right representing our abilities to as a national labs for the defense applications. Oh, sorry, I took the PowerPoint or the PDF version. Works as well. My division comes with a background from the semiconductor industry. As you see here, we worked a lot on semiconductor equipment, but more and more also on the device companies on the right. We help them, especially with metrology challenges, and I will come back to metrology more and more. But you see this portfolio also moving to the domain of quantum, of course. TNO started being active in quantum technologies more than a decade ago, when we started a collaboration with the University of Delft here close by. And just to show a few logos to give you an impression of the type of work we did. The first line, a couple of logos of partners from those early days already. Second line of logos is spin-off companies like Q-Blocks that originate from this kind of work. And at the bottom, a couple of logos from the companies that are either our customer or are even vested here locally in our ecosystem, where we already have a couple of hundreds of quantum scientists and engineers all together that really help each other. And on the right in blue, you see the current portfolio of TNO if it comes to quantum technologies. On the top, of course, applications in the defense domain. Think about GPS-free navigation, of course. The second block is more about the algorithms and the software and network security. And the red boxed part is my division, where we really focus on the physics and the hardware, both on quantum devices, QPUs, but also on full systems, which I would like to show you an example. One is the first European quantum computer we built a couple of years ago, called the Quantum Inspire. Really from the material science to both the transmon and spin qubits to the software connected to HPC, etc. It's a demonstrator project. It's not a huge computer, but it learned a lot about all the IP that is required and still had to be developed either by us or by our partners. So we learned a lot from this project. And to position TNO in the flow from academic research to industrial applications, here's an example. The picture on the left shows the device from my academic colleagues, 6 spin qubit device, really a hero device from the scientist. And with the help of TNO, we rebuilt and redesigned and reprocessed this device to the picture on the right. That was then the first spin qubit device ever manufactured at a 300mm fab. This is the one from Intel Hillsborough then. These days, we specialize mostly we get most requests at least by the spin, the qubits types here on the left. So semiconductor spins, a lot of NV centers and diamond, and the semiconductor two-pass, the amplifiers. What we think is really important that we contribute with is trying to stabilize all the processes. So with our background in semicon, we really focus a lot on characterization and stabilization of every process and every material in the full chain, something that is not common in the more exploratory academic type of research, but really we stabilize it, and it also helps to identify interesting white spots of new IP and IPR that we then can develop together with our partners. And as metrology is such an important topic, it is also quite a big effort on our side. So we have a whole suite of equipment, of course, the dilution refrigerators, but of course we want to test more and more also at room temperature and intermediate steps for fast turnaround and to stimulate the feedback from device performance to nanofabrication, because there's still a lot to learn and still a lot of IP to be generated there. And if metrology equipment doesn't exist yet, then we also like to develop it ourselves with our background in the semiconductor domain, where we have done this already for years. And this is just one example of a more public-private partnership, so that was not too confidential. And you see the partners that we work with here together. But contract research is really our core business, but these public partnerships help us to bring people together. And if you have any further questions, please let me know. And thank you for this opportunity.
Thank you, Roger. Appreciate the talk. One follow-up question for you is, as a nonprofit research institute, your organization's mission is to help rather than compete with companies. So what does a typical project with a company look like? How do you support them and what they're trying to do?
Well, I like best the companies that know a lot themselves and really look for complementary knowledge, because as the colleague already mentioned, no company or institute has all the knowledge available by itself. And we really look for complementarity. We have a broad portfolio and we help them with the bits and pieces that we are best at, and try not to be in the position of the company itself. So be complementary, that's the core business. Yeah.
Great. Thank you, Roger. With that, I'm going to introduce our last speaker before we open it up to the Q&A segment. By the way, if you guys have questions that anybody would like to see posed to the panel, please put them into the chat, and we can present them to the entire panel after this last talk. So I'm pleased to introduce Caitlin Moore. Caitlin Moore is a senior research physicist and leads the quantum group at SRI International. Her work focuses on cold and hot atom-based sensing and communication security research, including MEMS-scale devices, but she's representing larger quantum fabrication efforts at SRI in her talk. So I'll turn it over to Caitlin.
All right, so good morning. Thanks for the intro, Julie. My name is Caitlin Moore. That's right, Julie just sort of gave a bio of me. So thanks for that. Today I'll be outlining SRI's capabilities in quantum fabrication and prototyping. So what you kind of see there, the image is of one of our unique prototyping capabilities, actually, which is a miniature vacuum chamber employing a magnet-free ion pump. So I'll have a slide on that a little bit later. But so as you'll see, many of our offerings are sort of revolve around hardware and componentry, specifically developed for neutral atom quantum sensing and some related platforms. And so that sort of makes this presentation maybe a little bit different from the others. But nonetheless, SRI is sort of an independent, mission-driven nonprofit founded in 1946 by Stanford and sort of divested, became independent later on back in the 70s. And since then, it's acquired the Sarnoff Corporation, which was formerly RCA Labs, and then more recently our friends at PARC, so the Palo Alto Research Center, formerly of Xerox. So, so through that, we've, sort of built up a nice backlog of history and capability in advanced R&D. So we do R&D engagement in several ways, including licensing, some commercial contracts, quite a bit of federal funding, actually, funding through federal contracts. And sort of through these, we can collaborate with partners. I'm happy to collaborate with partners. So our capabilities span from sort of biological and education research through to more hardware-based and microsystems R&D. And so, of course, here today, I'll focus on capabilities we've developed relevant to the quantum community and specifically relevant to integrated quantum sensing platforms. So first, I want to start sort of generally by outlining our foundry type capabilities, which are sort of specifically relevant to optical devices found in quantum sensing and related hardware. For example, we have some sort of full wafer fabrication clean rooms. We have, staff with 20 plus years in custom high fidelity epitaxial growth. Fabricate on wafers up to 6 inches in diameter, some nice material sets listed here as well. And, we can also, achieve some high quality superlattices as thin as a nanometer, some layer thicknesses, over 10 microns is listed there. Show a nice picture on the right there of one of the superlattices, 3.5 superlattices. And, if folks want to sort of read more about that, you can sort of visit the website link here. We also have our group lead for that effort on the line as well on the panel today, available for questions. Some sorts of device types include DFBs, VCSELs, and QCLs, as well as some APDs, pin photodiodes, and optical modulators. So the offering there is mainly sort of a foundry type offering with sort of custom MOCVD growth, and it's mainly contract based. Okay. So next, I want to highlight some of our photonic integrated circuit capabilities. We have expertise that includes sort of a PIC design, layout, and test capabilities, and this sort of spans a variety of platforms, wavelengths, and applications, some of which are shown here. For example, there's a nice, we have a nice sort of single frequency violet wavelength integrated 3-inch laser. It's sort of shown in the bottom right-hand corner there with a paper reference if anybody's interested. But that's sort of a nice sort of heterogeneously integrated system on a PIC at a wavelength that could be relevant for something like a strontium ion, for example. And as well, we have, expertise in some quantum networking applications and optical phased arrays. But what our sort of atomic sensing group sort of most closely works with the PIC group on is some near IR waveguide platforms, including silicon nitride, for example, and some other material sets listed there. Because we tend to target these sort of nice sort of ground state neutral atom wavelengths, 780 nanometers being one of them. And we, can design for and also achieve both in-house and foundry fabrication as well. Capability to partner with several different foundries. So the offering here is mainly collaborative through a contract, and then I would certainly contact Dr. Kale Gentry or Dr. Thomas Winter, whose contacts are at the bottom of the screen there for more information. Great. And then finally, I'd like to dive into our anodic bonding prototype capabilities, which are fairly unique, nice offering, I think, in the community. These sort of three-dimensional anodically bonded vacuum enclosures for neutral atom or related platforms. The expertise here includes design and assembly capabilities for complex platforms, including silicon glass vacuum enclosures and robust optics photonics, or even electronic feed-through integration. You can see some example pictures on the right-hand side there. We have this nice enclosure that is sort of an epoxy-free vacuum cell construction for compact cold atom applications. We have a member on staff who's been doing this for over 15 years, sort of assembling these sort of custom anodically bonded prototypes. As well as shown in the sort of upper left-hand image there is sort of an image of an integrated magnet-free mini ion pump, which is a sort of a unique offering here as well. And then finally, recently we've achieved epoxy-free photonic circuit vacuum integration, which can also be sort of a hybrid magnetic photonic chip vacuum integration, also achieved via anodic bonding. And we have several pictures kind of shown, well, two different pictures rather shown on the slide here of that as well. If folks have questions on that, I would certainly contact Dr. Sterling McBride, listed on the bottom there. I mean, I can also answer some questions as well. And here the offering again is mainly similar to our photonic offering, which is more of a sort of collaborative under a contract kind of partnership. Okay, so with that, I'd like to thank you. Sort of an overall contact for any of this could be Greg Smith, who's our business development liaison at this email shown here.
Great, thank you so much, Caitlin. As one quick follow-up, a lot of those SRI fabrication services that you mentioned are focused, at least internally at SRI, at developing quantum sensors rather than qubits. So what types of quantum sensors are you seeing making the most impact right now?
Well, that's an interesting question, because in my background, I'm sort of more passionate about some over others. Certainly, there are some quantum sensors that I may not talk about in detail here that are sort of have been developed to such a high level that they're easily commercialized, for example, and SRI has some partnerships there already, which you can see in sort of the existing literature around optically pumped magnetometers. I think upcoming some of our capabilities offer are some of these nice vacuum envelopes could kind of open up the potential for fairly robust, almost getting there, wafer scalable type construction for cold atom based sensors, for example, which could potentially be a disruption sort of opportunity.
Wonderful, thank you so much. All right, that concludes the initial portion of our segment with the presentations from our panelists. And so I'm now going to move into the Q&A segment. I have some prepared questions for the panelists, but if people have additional questions, please put them in the chat and I will review them there as well. So to start off with though, for our first question, as I mentioned in my introduction, the last time we ran this panel was in 2021. And actually, Yuvraj from Rigetti was on that panel from 3 years ago as well. So my question to the panelists is, how has the fabrication and prototyping market changed and evolved over the last 3 years? And where do you see it going in the next 3 years? And I'm going to put that to you, Rob, first, considering that he was actually here 3 years ago.
Sure. Thanks, Julie. So yeah, 3 years ago, the landscape was quite a bit different. I think the biggest change we're seeing is there's been a lot of breakthroughs, open source breakthroughs in fabrication processes. So we've actually seen a pretty dramatic shift away from foundry services interest towards maybe full QPUs or Novera hardware. And I think this underscores the fact that universities even and PhD students and small scale labs are getting better at making quantum devices, but they're facing against the challenge of integrating this chip that they've made into a full system, like a full QPU system. So kind of moving up the stack away from the chip and understanding different parts of the componentry required. If you swap in different kinds of amplifiers, how does your performance change? Different kinds of shielding, different signal delivery mechanisms. There's a lot of talk in the field about going towards high density signaling, like away from coax, maybe towards flex cabling solutions or other cabling solutions. Transduction is another big area that we've seen pop up, probably spurred by the government's interest in quantum networking. So how do you, and if you can imagine putting QPUs in data centers around the country, how do you get them to talk to each other, right? How do you go from microwave to optical to microwave frequency conversion? So I do think in the next 3 years, we'll see the market kind of double down on this, zoomed out view, where there will be folks still researching the fabrication and design and more fundamental research about the chip side of things, but maybe more so on the integrated system side of things with, building out a QPU system.
Great, thanks. Jordan or Roger or Caitlin, do either of you want to comment on the market over the last 3 years and how things have evolved?
Yeah, if I may, and I agree to Yuvraj's statement, of course. One big thing, of course, is 3 years ago, it was still a lot of technology push from our kinds of institutes, motivating others that a few things were now finally possible. And now you really have companies that have a concept in mind or a strategy in mind, and they asked for their support. So that means that they have a vision on where to go. Having said that, of course, there's still no clear winner of the QED platform maybe, but there is clearly a market pool in that sense, which accelerates the developments and keeping scientists from being distracted too many fundamental aspects. Second point indeed is what we call system engineering. It's no longer about just the QPU and showing that you can build the first one, but it is how does it work together with all the software layers, the cryogenics, etc. And just like in semiconductor industry, the interfacing, the interconnecting turns out to be a really critical one. And I see quite a few institutes and companies working on this. And a third one is that we see a professionalization in testing and characterization. Is no longer just a lucky shot or a hero device, but you have to be able to repeat. I see you nodding, Yuvraj. You have to know what you do, so you need more metrology and even more metrology equipment. And we even have quantum sensors now to measure whether the nanofabrication was successful. That kind of developments. Jordan, maybe you can add?
Yeah, I couldn't agree more that is the push, that we need to go towards more stability and more metrology and really trying to make something that actually not only works, but you can produce it at scale. One thing that we have noticed quite a bit also has been the growth of these so-called fabless quantum computing companies, where they actually outsource quite a lot of their fab because they see their competencies in design and figuring out this full stack integration and so on. They don't want to build their own fab. It's quite expensive, and maybe they don't have the volumes required to build their own fab. So they want to outsource that so they can be a fabless system integrator or designer, which is quite interesting. And this is somewhat aligned with, at least in Europe, I can say we're going. So Europe is investing quite heavily in the next 3 years in developing a pan-European stable pilot line. So there are government-backed initiatives really to try and offer services for the companies to be more or less fabless, that there will be some way for the companies to ask on a European scale, can you make this product for us so that we don't need the tens of millions to make our own fab? I find to be quite interesting. I hope we manage to make some progress towards that in the next 3 years.
Wonderful, thank you. I'm going to move on to the next question, which is, we have a fairly high significant representation from nonprofit research institutes in this panel. What role do nonprofit research institutes play in shaping fabrication and prototyping market that might be different from a commercial vendor? And I might send that over to Caitlin first to comment.
Sure. Yeah, I'll say that our role as a nonprofit tends to be as sort of a collaboration builder almost. So we tend to sort of connect maybe nascent R&D methods from university with also maybe more mature or focused sort of R&D efforts from commercial entities. And sort of try to roll all of that together towards a single solution that might, satisfy a contract or a bid or something like that.
Jordan or Roger, you want to comment?
Sure. Well, I think, as already said previously, that the role of the not-for-profits and government research labs in general is to not compete with the companies. We're there to enable the companies. So then we don't need to make a profit. So we're really not in competition. We're there to figure out what is it that we can do differently or can do that the companies cannot do, and really go in that direction to enable them in the future. I don't know if somebody else has something to add.
And I want to put a question to you, Raj, which is, how does a for-profit company like Rigetti work with nonprofit research institutes?
Yeah, I think research institutes in general, whether they're nonprofit or otherwise, are critical to the development of the quantum industry. I think a really good example of this is the SQMS. So it's Superconducting Quantum Materials and Systems Center. This is led by Fermilab, but it's in Chicago area. But it's a consortium of many universities, many other national labs as well, and industry partners, including Rigetti. And each one of these entities brings a different strength to the table. So, academic groups have a lot of creativity. They can move very rapidly with experimentation, but they cannot scale. We, coming from industry, we might not be able to move as rapidly as a small group, but we can scale, and we also have the ability to experiment with many different device types in parallel. And then finally, the nonprofit research institutes, they bring a lot of know-how, right? There's probably cumulative, many decades of experience with these researchers there, and kind of help bridge the gap between, I like to say, from lab to fab and then beyond, right? So how do you bridge the gap from lab to fab to large scale manufacturing? And I think this three-way combination is key towards making that happen efficiently.
Great. Taking a few questions that have come out of the chat here and kind of synthesizing them. A few different people have asked about more exotic materials, either magnetic materials, quartz as a materials device, or using more exploratory types of etching, like cryogenic ALE. So the question for, I guess, across the board is, if a company wants to explore one of these more exploratory either materials or processes, how best can they work with your institutions? So I'll start with Rigetti, because I think you have some of the most rigid requirements, and then we'll move into the research institutes.
Sure. Yeah. So one of the key things underpinning our Foundry services is we want to offer what we know works, right? So we're constantly experimenting with different, substrates, materials, fab processes, you name it, right? We have our own fabs, so we have the flexibility to do that. And whenever we have validated something on first, small scale test chips, get some qubit statistics, understand what effect it has on the device performance, scale that up to connected lattice of qubits, so a small scale QPU. This 9-qubit QPU that I talked about, the Nevera, that's actually our internal R&D test platform as well, before we scale anything up to the 84Q scale. And then once it's validated at the 9Q scale, then we would start offering it in our Foundry services. So we kind of have this phase gate process where we want to make sure that what our custom design customers and partners are using is the latest and greatest. Now, there is maybe a small asterisk on that. You know, we do partner, like I mentioned, with Fermilab and academic partners that want to experiment. They're the kind of our R&D partners. So for them, we might have expanded access to our PDK, where there might be materials that we don't use in our process of record that we would be open to experimenting with. But that's very much in the under the umbrella of a research collaboration, for example. So actually, a good, if folks want to look this up at some point, a good example of that is the work we did with Fermilab on encapsulation. So we basically figured out ways to encapsulate niobium with other materials to improve qubit performance. And that was a great example of how our Foundry services could be expanded for key research partners.
So I want to now put that same question to the research institutes. How do you guys deal with more exotic materials that may not be part of your standard processes if a customer was interested in exploring those? Roger, Jordan, or Caitlin, you want to comment?
I can say add a few things. So I recognize the challenge. For some of the processes with really new materials or risky materials, we also work closely together with university, where we can have some equipment where we dare to use new materials that might contaminate. So we keep control over the process or the whole project, but we use the academic colleagues, because there you sometimes have equipment where you can explore a little bit more. Indeed, before you go transfer it to a colleague institute with more like a foundry or a pilot line model. For example, cobalt, and we work quite a bit on magnetics or magnets on spin qubit devices. Yeah, that is possible in this kind of settings that are otherwise not possible.
Jordan, do you have any comments? And what about new fabrication processes as well? So if you need new tools or other things to do lithography or etch, rather than just new materials.
Yeah, on the material front, it's something similar to what has been said, right? So we have different tools with different material restrictions. So, for example, we don't want gold anywhere near our CMOS line, and for example, in other applications, gold is perfectly fine, right? You want to put gold for your contacts, so we keep the tools very very separated and have contamination controls. And similarly for the superconductors, we don't want to put anything non-superconducting anywhere near. So. Yeah, so we just try to control it, and then we always do a risk analysis of every material we bring into the clean room, and decide on a case-by-case basis. But usually, I think the question was in the context of magnetic materials, and I think those are in general not going to enter our clean room anytime soon, not without some radical changes to the way we operate. But then in terms of developing new materials, that's something that we are really excited to do and are always active to do it. And we are always partnering with the universities, but also the tool manufacturers to develop new processes and make devices from those materials to find applications. I think this is super exciting, and that's really behind a lot of our development, that we can offer these new materials and take multi-year projects to really bring them up to the level where they can be used for something.
Okay. Any other comments?
Yeah, so Julie, I have David on the line as well. He leads one of our fabrication groups. I'd like to let him comment as well.
Sure, go ahead, David.
Yeah, hi everyone. I mean, so I think one of the advantages of being sort of a nonprofit where we don't have existing product lines that we have to worry about not contaminating is that for these much more exotic things, we're kind of willing to try it out. You want to try a magnetic material, you want to try a gold and silicon, you want to try some weird combination. Generally, we're amenable to doing that kind of research.
Great, thanks. I'm going to jump ahead to a question about, in general, what's currently happening in the quantum sensing market. So we've noted in this panel that quantum computing architectures have matured. And so are there any indications in the early fabrication and prototyping market of a shift more into quantum sensing, and which sensors are generating the most interest? So I'll start by putting that question to Caitlin. She touched on that earlier, but I'll let her comment again, and then turn it over to others.
Yeah, I'm happy to. Thanks. Sure. Being what I do research in, I'm not so much sure of a shift as sort of continued interest, especially from OUSD and sort of more DoD related applications. Sort of continued strong interest, I would say. And that's sort of, that's sort of evident from sort of publicly available sources. I would say, certainly sensors that generate the most interest tend to be sensors that sort of work at a commercial level now. You can maybe buy them off the shelf. And from a neutral atom standpoint, that does tend to be, sort of magnetometers, atomic-based magnetometers, right? Up and coming, of course, we see sort of the usual, right? We see atomic electrometers, and then maybe following that, we see sort of cold atom-based, maybe inertial sensors or something like that. But of course, I've seen also folks on this call even who may be developing squids as well. Another sort of magnetometer. Potentially folks want to comment on sort of the non-atom-based quantum sensing types that they have in their arsenal.
Roger or Jordan, do you want to comment on the quantum sensors that you guys are working on and where you see the most excitement?
Sure, my pleasure. Yeah, we work a lot on the NV centers in Diamond because that has a significant volume in the application of quantum communications and in the future of quantum repeaters, but also some types of quantum computing. So that generates let's say the critical volume of people and resources to develop this kind of material platforms, and by that we can also make sensors out of it. For example, magnetometers. And once you know this basic material platform pretty well, you can have different types of applications. So I mentioned already GPS-free navigation based on this kind of quantum sensors. But we also use them to probe magnetic or electronic properties of devices, both in the quantum domain, but also we're now testing in the semicon domain. So it really opens up a new set of possibilities. But in general, the quantum sensor is always a difficult challenge, a question in this kind of settings, because indeed there are so many sensors and you can have really full understanding of just a handful, and I can definitely not cover the whole portfolio.
Sure. Jordan, do you want to comment?
Yeah, it's also hard for me to pick a favorite from the ones that we are doing. But I would say, actually, I think it's very interesting to see how the sensing market and the quantum computing solutions are growing together, right? So quite a lot of our expertise on making superconducting films for QPUs actually came from making squids and things like that. We're actually trying to use the developments we made to make squids. For example, the junctions themselves that are etched junctions in our squids. Well, can we deploy that for the QPUs? And now we're seeing that the developments made in QPUs and enabling technologies for quantum computing being useful for the sensing market. So things like parametric amplifiers and solid state switches and things like this are absolutely essential for doing highly integrated sensing solutions. So I do see the two fields working quite closely together. And for example, material development for making high kinetic inductance detectors might be useful for making more dense quantum computers. I don't know, but I think it's exciting to see how they can grow together at this point.
You, Rob, do you want to comment on sensing at all?
Sure, yeah. So fundamentally, qubits are really high precision sensors, and you can tune them to whatever frequency you want to sense at. So that's actually something that has come up a lot, maybe the past year or two, when folks have been asking, hey, can you leverage your superconducting device fabrication process for quantum sensing devices? So things like TESs, right, transition edge sensors. There's series squid amplifiers that are used in cosmology and particle physics detectors. So we have been exploring those opportunities primarily in the vein of research collaborations. But I think one good example of that is we did an experiment with Gran Sasso in Italy, where we created a custom device where we tuned the qubits to be very sensitive to cosmic rays that were incident on the device. So we basically were able to use a a qubit device. I refrain from calling it a QPU, but we used a qubit device as basically a cosmic ray particle sensor, and this was used by the particle physicists over at Gran Sasso. So there definitely is some dual use there between quantum sensing and quantum computing. It's just for us, we are very focused on computing, so we want to make sure to stray minimally from our core roadmap.
Great, thanks. So we are at the top of the hour at this point, so I want to take the opportunity to thank all of our speakers again. If I didn't get to your questions in the chat, I think our speakers will be typing answers back and making those available as part of the wrap up later. But thank you everybody for being part of our discussion today, and enjoy the rest of your day.